So welcome everyone. We are here at the Commission G5 talks, and we have the pleasure today of having Katharina Lodders, who is a well-known expert in the compositions of the solar system bodies and astrochemistry in general. She did her PhD in 1991 in Germany at the Max Planck Institute for Chemistry in Germany. And after that, she moved to Washington University in St. Louis, where she's currently a research professor, or has developed her career. She was a project officer for the astronomy division of the National Science Foundation between 2010 and 2013. And she's the lead author of 2 books on astrochemistry, and has written over 100 papers, very well-cited papers, astronomical research on this topic. And she's going to tell us the latest news on abundances of meteorites. Katharina, welcome.
Thank you for having me. Let me share my screen. Go to the presentation view. Okay, let's try to get here. Well, good morning, good afternoon, good day. I'm glad to be here. I will tell you today a little bit about the quest for the solar system elemental abundances, give you a very brief update on the latest photospheric abundances that we have done in collaboration with Herbert Palmer and Maria Bergerman. I will focus a little bit on the abundances of CI chondrites and related asteroids, and conclude with a summary of a wish list of what needs to be done. Just for the nomenclature, I use solar abundances mainly to concerning elements related to the sun directly, and solar system abundances for the overall composition derived from meteorites and the solar abundances. And in most cases, it refers to the protosolar abundances at the beginning of the solar system. I also would like to note the 2 papers where we have updates being summarized. So now the question is, of course, why do we even care about solar system abundances? There are many aspects where the solar abundances pertain to. It's how the sun works and evolves. We want to know about the composition and formation about our solar system, other solar systems, planetary compositions. It's a baseline reference for any type of abundances. You typically normalize to solar. Then importantly, the abundances were an input and gave ideas to models of nucleosynthesis, and remain a test for models of stellar evolution and element nucleosynthesis and galactic chemical evolution. So there are many reasons, and one reason why people started looking at it, it's the stuff we are made of, and we want to know where it's coming from and how it's been made. The quest for the elemental abundances and their origins dates essentially back to the time when meteorites were recognized as being extraterrestrial. That started in 1795 when Chladni said, hey, meteorites exist. That was a big debate and big controversy at the time. Then during the time, also a lot of the chemical elements, the chemical periodic table was essentially populated with new discoveries. And there were already sketchy analysis. You couldn't do much quantitative with the old analytical method, but it was found out 16 abundant elements are common to the Earth and meteorites, and also common to meteorites. Meteorites were considered very early. Then it took a while to get the spectral analysis going. And in the interim, I point this out here. I note when some meteorites, the CI chondrites that are very important, actually were observed to fall. Well, the periodic table came in, and then people realized the element occurrences in celestial objects are not random. And then in 1889, we finally had the Earth's crust abundances. And what was known at the time it came about to be realized, the elements with atomic numbers up to iron are abundant, heavier elements are rare, and the notable exceptions are lithium, beryllium, and boron. Then the story continues and we go into the next century. The question was, how can we even know the universal composition? Well, G.P. Merrills said, let's use meteorites as world-making materials. The notion at the time was still that everything else in the universe must be of composition like the terrestrial planet, like the Earth. It was all Earth composition centric. Well, that game continued, and it was quickly realized some meteorites with their metal, sulfide, and silicate, they must resemble the bulk Earth, and the Earth is of course differentiated into a silicate crust and a metallic mantle, and in between a silicate mantle, and then of course a core. Then there were finally enough data that you could discern the odd-even effect, and you needed meteorite data to show that, because the terrestrial abundances are of course fractionated due to chemical differentiation. So then we finally got on, and 100 years, and I don't know if we had actually a big party about it, that the first stellar abundance analysis happened by Cecilia Payne-Gaposchkin. And the recognition that hydrogen and helium are actually the most abundant elements in stars and in the universe. Finally, also about that same time, all stable and long-lived elements had finally been discovered. And then Cecilia's advisor finally put together the first comprehensive solar photospheric abundances in 1929. At the same time, Victor Goldschmidt, he was highly influential in geochemistry, but he should also be recognized for astronomy and nucleosynthesis. He worked out the composition between Earth's crust, Earth versus the total Earth versus cosmic abundances. And he, in his 1938 paper, he takes ahead a lot of insights that later on became important again. I think he even had ideas about the nuclear shell models and observations on nucleosynthesis. And one of the most key important things was that the distribution of the elements is controlled by electron shell properties, the valence of the chemistry, but the origin and abundances of the elements were controlled by nuclear properties. Now, after the Second World War, things continued. Hans Suess picked up on the theme that Goldschmidt had. He came up with nuclear abundance rules and found that the distribution curves of the isotopes is relatively smooth, and that can be used also to estimate the abundances of elements and isotopes from interpolations. That game is still played today and dates essentially back to Goldschmidt. Then the question still was, yeah, well, how do we get cosmic abundances? There were still attempts to get that from weighted phase composition. So you analyze the silicate, the metal, and the sulfide from meteorites, make it a weighted composition to match Earth's bulk density, and that's then the cosmic composition. Well, people smarted up and said, well, let's use the chondrite compositions. These are meteorites that are undifferentiated. And let's take the meteorites as they are and combine them with solar abundances and do interpolation. This table by Hans Suess and Harold Bury was very influential because it led to the insight and stimulated the nucleosynthesis models by Burbidge, Burge, Fowler, and Hoyle, and of course Al Cameron. Then this time was very busy and people had more material to analyze, better analytical technique, and that was very important. And it became clear that, let's take subtypes of the primitive meteorites, the so-called carbonaceous chondrites. And the first paper that I could find that really advocates for carbonaceous chondrites of the Ivuna types, the CI chondrites we all have heard about, was done in 1906 by Reed, Kiyogashii, and Turekevich. So this became more and more standard. Let's use the CI chondrites as solar abundance proxy, for the simple reason that a lot of the abundances of the volatile elements that were measured were matching the predictions from nucleosynthesis, nuclear interpolations again. And they confirmed what was long predicted. And then in 1968 and 73, Al Cameron finally came out with the first abundance tables based on solar and CI chondritic data. There was, of course, a problem, and I don't know how many of you might remember this or know this story. For a long time, there was a division between the astronomic and the meteoritic communities because one of the major elements, the iron abundance, was too low in the sun and did not match with the meteorite data. And of course, you want to make sure that if you say it's a solar system proxy, that solar and meteoritic abundances should agree for major elements. Well, it turned out that the GF values were not determined correctly in the lab. There was some calibration problem with a furnace or something. Well, it turned out that problem was solved, and iron abundances matches perfectly to the solar iron abundance matches perfectly to the meteoritic data. And Ed Anders wrote a big paper in 71. Yes, let's use CI chondrites. They are the best match to the solar data, and they are the most volatile element rich to compare to other chondrites. And so since then, we use CI chondrites as abundance standard for elements more refractory than water ice. And we're still doing this today. Now, this diagram is fairly busy, but this is the current situation. What I've plotted here are the abundances on an atomic scale relative to 10 to the 6 silicon, and versus atomic number. The yellow dots are photospheric data and also includes a few data for the which are derived from sunspots. Sunspots would be nice to see more and better determination for fluorine, chlorine, indium, and thallium, because these are all volatile elements that are very important for planetary and modeling. Then there are some solar wind data, neon, argon, xenon, and krypton. However, they are also in part based on nuclear interpolations and element ratio, and hydrogen and helium are, of course, derived from helioseismology and standard solar models. And the important thing is that the sun is the only reliable source for abundances of the highly volatile elements HC and O and the noble gases. These volatiles only form ices, and ices are not retained on meteorite parent bodies. And we are not keeping these elements, even if they were ices accreted to on meteorite parent bodies, they will not survive on Earth. So if you measure meteorites, there's no way of getting those. But the problem with solar abundance is, of course, that the uncertainties are typically larger than for meteorites. There are error bars plotted on this diagram, but I made the symbols bigger so that we can see what it is. And you see the orders of 12 orders of magnitude that the abundances normally span. So there's no way that you see the uncertainties here. The blue data points are the meteoritic data, and you can nicely see what stands out. the noble gases are, of course, depleted in meteorites, not retained. Oxygen, nitrogen, carbon, hydrogen, oh, here's the helium, I forgot that, is also lower. Lithium is higher because lithium is, of course, destroyed in the sun. We know that. And otherwise, for the elements on this scale and this compression, you see, yes, there's a relatively well overlap in the yellow and blue dots. That's the key point of this graph. We also see that there are some elements here, and they are also very important because it's moderately volatile to volatile elements for which we don't have any solar data. Arsenic, selenium, bromine, antimony, that's high on my wish list, tellurium, iodine, cesium would be great to get better idea. Tantalum, rhenium, platinum, mercury, a problem child in any kind of object, lead, bismuth, thorium, and uranium. These are not very well determined in the sun. So how do we get there? As I already mentioned, that all started early on. The problem with the solar spectral analysis, the problem is you're having an object and you cannot standardize it easily, so you have to make up a 3D model of the solar atmosphere and use radiative transfer modeling. Then not all elements can be quantified. I think there are about 60 of 83 elements that you can get. And one stumbling block are the relatively large uncertainties, typically 20 to 50%. What we have here, what we did in our recent paper, the solar work was mainly done by Maria Bergemann and her group. And I can only touch on a few things. I'm not the solar expert here, and you probably know more than I about this, but we have documented our approach and analysis and discussion for all the elements in our recent paper, and I can only refer you to that for more details. The key message is that we have currently 16 elements with full 3D model and non-LTE analysis. They are listed here. These are the best determined elements in the sun as it stands. There are many recent improvements and more revisions are forthcoming, and I'm really looking forward to this because there's a lot of new atomic and molecular data, new solar model atmosphere, and new observational data also from yeah, and one important result was also that overall abundances are trending to higher values again after the early 2000s, where the metallicity was dropping tremendously. We are getting back to higher values. Here again, just this is a table we have in the paper. So we also introduced, I only wanted to point this out, we introduced some quality tag flags using the college grading from A to E here in the quality index. And there are a few elements, mainly those with 3D and non-LTE, that we gave a quality index of A, but the uncertainties often are still large, 12% or so, which I think is the best assessment that one can do right now, considering all the input and uncertainties that go in there. There are differences between the abundance sets between our work and Martin Asplund and his co-workers. And there are various reasons for that. That is in atomic data, that is in the non-LTE approach, then the 3D models and in the observed solar spectrum. And what I found actually quite surprising in this whole thing, that all these changes tend to increase the abundances for several elements. What is shown in this diagram is the ratio where I set hydrogen to unity versus atomic number. And this is just our abundances compared to the Asplund et al. Abundances in 21. The bar is about 26% or 0.1 dex equivalent uncertainty. And you can see that all the red dots that's the elements we looked at, while there is agreement for some, because we all have to take the same data, there were many elements for which we obtained higher abundances. And would be interesting to look at some of the other elements as well. There are also some problem elements in this mass region here. Would be nice to get this. But the main reason, because these are the more abundant elements, they determine they have a large influence into the heavy element fraction. That's why the metallicity has been going up. Now, the higher metallicity, of course, has good news because it restores and improves agreement with standard solar models. Again, we all remember the oxygen crisis, and I think that is towards a resolution. And the effect also has, when we link the solar and meteoritic abundances, which are typically derived on different scales, and you have to couple the meteorite data to the solar data. We cannot use a hydrogen scale for meteorites because hydrogen is depleted. So you typically take one element, silicon, and say we normalize both scales to silicon and then combine the abundance data. We prefer to use an average of well-determined major elements for the simple reason that this gives a better and more robust coupling factor. Because if you change the silicon abundance in the solar or meteoritic set, you would have to renormalize everything and introduce a scatter from this. And we figured this gives more flexibility and also a more solid link, because who knows if the silicon abundances, for example, would be really correct. This, because we have higher metallicity in the solar data, the coupling factor here is 1.55 that you have to add to the log of the meteoritic abundances to get it onto the solar scale, is higher than in some other compilations. This also then affects elements that you have to derive by interpolation, because if your neighboring element or isotopes have a higher abundance, the element that you get by interpolation will also be higher. This explains the differences that we have in some elements like krypton and xenon, or in the oxygen-neon ratio and such. Now, I wanted to go to the meteorites. And the meteorites, if you look at this hydrogen, helium, then CNO and neon, that is the bulk of this solar material. Sodium to nickel make only about 22% of that, of the heavy element fraction. And all other elements are only 0.02%. And these abundances is where the meteorite data come into play, where we can get better and more precise measurements. Now, as I already mentioned, there's so many meteorite types. Now, what to use? Well, you don't want to use differentiated meteorites. That cannot be, because there's clearly some chemical fractionation. Let's look at chondrites. I don't know how familiar everybody is with meteorites, so I'm showing just a few main major points here. Chondritic meteorites, there are several different groups, and called ordinary chondrites, because this is a meteorite types which fall down the most. Then there's some ancestral chondrites, and then there's this huge group of carbonaceous chondrites, which is has many subgroups. Many chondrites contain mineral phases that closely resemble that what you expect to form in a solar nebula, like silicates, metal, and sulfides. one exception for that, not showing those dry materials are the CI chondrites. And many chondrites, hence the name, contain the little round spheres that you can see here and here in the thin section. These are the chondrules, and hence the name chondrites. While CI chondrites are also an exception for that, they don't have chondrules. And this is a statistical plot. This is the observed meteorite falls to date, where we have samples of ordinary chondrites, and you see there's mainly ordinary chondrites that are come down, and Enstatite chondrites are few. In total, we have about 1,000 non-carbonaceous chondrites. And then we have only 56 carbonaceous chondrites, and among all these chondrites that have been seen to fall, there are 5 CI chondrites. Of course, the group that we are interested in is rare. Why are we so interested in hyping about CI chondrites also? All known groups of chondrites show depletions in volatile element relative to CI chondrites. What is shown here, and the point of this diagram is, no matter what you plot, here, for example, I have the CM chondrites over CI chondrites. Every diagram is normalized to the same set of CI chondrite data. And I plot it as a function of condensation temperature. And what you see, refractory is high, volatiles low. Refractory is high, no matter in what chondrite group you look, they are all depleted in volatiles. That means that the CI chondrites are the most volatile rich. And that was a key point in singling them out among the meteorite groups. They appear the most volatile rich material that we can get our hands on for the elements more refractory than water ice. And you also see the green dots, blue dots, and yellow dots. It doesn't matter. This indicates the geochemical character. It does not matter if the element is present as a silicate phase in green, or as a metal phase in blue, or as a sulfide phase. The fractionation is volatility controlled. It could be a condensation evaporation process that is still under debate. You can find more in the paper that is referenced here. We went through this and also have updated condensation temperatures there, and some ideas how you actually should use condensation temperature, because this is a very oversimplified view. Now, the other reason why we pick CI chondrites, they are closest in abundance to the sun. Of course, on a log plot, it's not difficult to get a straight line. This line is a one-to-one correspondence line. And this is the best view where you can make the comparison. It's the CI chondrites that provide the best fit, except for the volatile element and lithium, of course. Then we also find that among all the chondrite groups that there are, here's my chondrite groups again. And here I plot the element magnesium ratio normalized to the sun, which means that the sun plots for all elements that I'm plotting here, and I'm plotting aluminum, silicon, manganese, and sulfur. Sun plots here. And then I want to see which meteorite group matches the best to the sun, and it's CI chondrites. Their element magnesium ratios are closest to the one line here. You could say, oh, wait a minute, here's somebody, the EH chondrites, they are also plotting along unity. This is good. But the problem is that the silicon magnesium ratio of enstatite chondrites is much higher than that what you have in the sun or in carbonaceous chondrites. And it is mainly this exception, a few other elements, that rules out that the enstatite chondrites are making a good solar proxy. Now, to move on, the other thing that is very important is to point out, when you look at the elements and you in a nuclide chart, you convert the abundances to isotopic composition. You make that into a typical Zeus plot, and you plot the isotope abundances. You see that you get this nice, relatively smooth abundance curves. When you see your R process peaks, your alpha elements, the iron peak, and so forth. You see all the details that stimulated later on the ideas about nucleosynthesis. And the color coding here is for where an element or the isotope would sit. Sits it in a silicate or in a metal or in a sulfate phase. And if there were any kind of chemical fractionation, like you would remove a sulfide bearing phase, then these yellow dots would not fit in smoothly into the curve. Okay, so that wouldn't work. Or if there were a metal fractionation, you would disturb the continuity among the green and the blue dotted lines here. So that is another indication that we're dealing with primitive material from the chondrites. Now, the chondrites are not the typical chondrites. They don't have chondrules. They are mainly phyllosilicate because they experienced aqueous parent body alteration. So it's not only that these meteorites accreted early material that formed in assembled in the solar nebula, but the parent body also accreted water, and that water melted and changed our mineralogy. Now, the mineralogist will tell you that it's a highly complex rock, but in terms of chemical bulk composition, they are primitive, and that's the key. They are only primitive in elemental overall composition, but not in mineralogy. They are very complicated. The fact that they accreted water ice also means that you would expect that all other elements that are more refractory than water ice would have condensed in the rock. So this is also another indication that it makes sense to use CI chondrites. And here are 5 CI chondrites that we have available. They have been on Earth for a long time. And this Ryugu meteorite, you probably have heard the name, that fell in 1864, has the most mass. This is the best analyzed rock among them. I want to mention here, we just found a new meteorite last year that is being analyzed. That's a fresh sample, apparently, despite being a find. So there are more new data coming, so we have new data here. The key point about aqueous alteration on the parent body is also that it does 2 things. It homogenizes the composition very well, so that is good news, because you always wonder if you have different phases, mineral phases present, how can you be sure that you have an average representative composition? Because the salt formation that also happens might also introduce heterogeneity, because there are some elements that love to go into these minor phases like phosphates, carbonates, sulfides, and halides. Now, that is long known that if you analyze 50 to 200 milligram of a well homogenized sample, you take 1 or 2 grams of meteorite, homogenize it, and do your analysis, you get really a good representative sample. There are also some geochemical tools to deal with that, but we are pretty sure that we are able to get well representative average analysis. Now, these rocks, there's always a catch. These rocks have a trouble that they're also very, very sensitive to the terrestrial atmosphere. So if you go into the museum, into the Smithsonian in Washington, that's where I took these diagrams, and you look at the Ryugu meteorites, this is a sad picture that you see. Even if they are stored in a container and supposedly not getting much exposure to air or humidity, they crumble. As soon as they see the air, they crumble, they oxidize. You see this white material here, that is some efflorescence. They are reacting with the Earth's oxygen, and this is fostered by humidity. This affects the oxygen and hydrogen content, and it changes the absolute concentration because you're diluting it a little bit with water and oxygen. But the effect on abundances is not there, because abundances are ratio derived, right? You're always normalizing to silicon or magnesium. You always look at element ratio when you talk about abundances. In a solar case, it would be your element hydrogen ratio. So abundances is always a relative quantity. And we know that this affected, again, hydrogen, carbon, nitrogen, oxygen, which we already know we don't have the full complement to begin with for these elements. So the whole change in oxidation is isochemical, but element redistribution within the rock are possible because you see this white stuff here. This is a rock that is stored under nitrogen, but it still develops efflorescence. So material is transported with water through the rock and deposited. So you again have to watch out during your analysis for to get a well average sample. There's also the possibility if you have a meteorite sitting in a museum or in a desert or in the laboratory that there's pollution. And okay, the main pollution that is known is this plant pollen and mercury. For other elements, there might be individual small fragments that are known to be contaminated, but otherwise we have no indication that there's any abundance issue that was introduced by contamination. Now, all these problems are being erased with terrestrial alteration and contamination because we now have two asteroid missions, JAXA's Hayabusa mission to Ryugu and NASA OSIRIS-REx to asteroid Bennu. And it turned out this was really unexpected and really great. These are essentially pristine CI chondrites. And the first analysis indicate there are no major changes for the meteoritic solar system abundances that we have derived from CI chondrites. And the other good news is that we will be able to do refinements. And I'm really hoping that we get abundance improvements for the halogens and some metallic xerophile elements and also some chalcophile elements. These data are coming in. We are working on it, and we also have some samples in a lab at Wash U where we are in close collaboration. So all this is great news, and it also the first results really give us confidence that the chondrite data that we do have are very good. Now, how do we get this data? Just briefly, these are the references we went through. That's a lot of references and data to crunch. And I'd only want to give you an example. How do all the data that you get from the CI table actually derived? We have all this described also in our recent paper. So we collect all the data, for example, for nickel that are available. We do that for each meteorite, for each carbonaceous chondrite. Here, example for okay. We check the analytical methods. Here, I give an example there. These are all the neutron activation analysis data. Here are the data from ICP-MS, different analytical methods. This is all the data that we have. This is the distribution you get. If you put all the data from all CI chondrites together, you get this distribution. Then you screen this for all the different methods, and we're typically not using the old wet chemical data from the 1800s or data that have large uncertainties like calorimetric or flame photometry data. Once you do this data screening, you are left with this distribution. And then you look at this, and if you apply some statistics and look at this, you can get a distribution that has 2 or 3 modes in them. You have a low mode, a main mode, which is the number of the nickel number that you will find in a table, and then there might be a high mode distribution. These in old days, it was always a question: is it an analytical issue or not? And you really need a fair amount of data to discern such distribution. If you look at only the neutron activation or the ICP-MS data, you might get the idea maybe there's something going on with bimodal, trimodal, or something. But this is clearly the case and can be understood. This distribution is understood with the chemical processes that have happened on the parent body and terrestrial redistribution. That's well understood. And let me show you some other cases. You will also find that in the paper for elements that are easily water soluble and therefore mobile on the parent body and in the museum. Here's our nickel example. We looked at that just a moment ago. And we see this for sodium. We all know salt, sodium, potassium, rubidium. Interestingly, cesium is not doing such a behavior. And we also have magnesium, calcium, strontium. These are elements that like to be in salts. We also have elements like barium, thorium, where we have a little bit of a different distribution, where we see a main mode, and then we see what I call the trailing distribution, or where we have some samples that seem to have high barium, thorium, a few other elements doing the same thing. And we know that this happens when you have a phosphate in the sample, because phosphates love to collect barium and thorium, for example. There's also some other elements that also tend to show this distribution. Again, this we can all understand if we consider the chemistry ongoing, and but it is this effort which we did for every element, and I can tell you there are lots of elements, to go through to derive the best CI average composition. We also have, and now this is the first data that are summarized in a paper by Yokoyama on asteroid Ryugu. We can play the same game with the asteroid sample, and you see there are subtle differences for sodium, for example. In CI chondrites, although not very convincing, there's a low mode which seems to be missing in the Ryugu data. There are some subtle differences. There also seems to be a broader peak for magnesium, and there seems to be something else going on for calcium. There seems to be more calcium-rich sample, which is understood because there's a lot of carbonates in Ryugu. All that is also understood, and the problem is these are very small samples. We're talking a milligram or less sample, and there, of course, you can have a mineral phase dominating the analysis easily. And here you have typically samples of much larger, and finding an outlier sample is relatively rare in comparison. And let me move on. Overall, we have CI chondrites, Bennu, and Ryugu data. There are issues with the element distributions from aqueously mobile elements. And what I'm showing here is the red circle is everything we have no solar data on, solar data that have a larger uncertainty. And in order to get these elements, we need to use meteorite data. However, the meteorite data, which are encompassing also aqueously mobile elements, as in a blue circle, also contain elements which are not very well measured, where we need more measurement also from the asteroid samples to understand the distribution better and refine the numbers. And then there are volatile elements where we also need to do a little bit more work to understand the data. And you see no good solar data, aqueously mobile and volatile is a set of elements that is really interesting and important for planetary modeling. I can't go into more detail right now because time is of the essence. I only want to show you how all the data compare. Here the individual meteorites and asteroid data are normalized to the average CI chondrite composition, or G is dominating the set. So you see that is very close to unity, and the halogens being outliers, and same for the Ivino meteorite. The Bennu sample, there's more scatter, but we only have a handful of samples analyzed. the new meteorite that was just found, again, this is based on 3 analysis, so scatter can be understood. The Alley meteorite, which is the first CI chondrite that was found, surprisingly shows in the overall pattern some similarity to the Ryugu data. But again, the Ryugu data is based on small samples sizes, and more analysis need to be done. But overall, the story is converging. Just comparison to the solar photosphere, you see everything is here in the gray bar would be 25% agreement. This is the state of the art. This is the current, our recommended CI values relative to solar. And what you can see, the elements that are very well determined in the sun show a good agreement. This is the green dots here, that's the 3D non-LTE data. The new meteorite, Bennu and Ryugu data, this is as good as it gets. I'm expecting a lot of improvements for these and also for this meteorite. The solar, rhodium, silver, and palladium, that would be nice to get this being taken care of. I don't know what can be done. In the interest of time, we can talk about that during discussion. There's always been the question now, are CI chondrites and the photospheric data fractionated, yes or no? So I'm plotting the CI chondrites over the photosphere normalized to magnesium as function of condensation temperature this time. And I'm not sure if I see a trend here. And if the bright data spots here, these are the elements that are well determined. Let's go back to here, this diagram, which shows only the elements that are well determined as a function of condensation temperature. And what is plotted here, the chondrites over the photosphere. If it weren't for the aluminum number, you could say, maybe there's a small trend, I don't know. But the refractory elements within 25% or better, I'm not sure that there's a trend. That from the data that we have looked at, it cannot be said. Then it has been suggested that maybe the CI chondrites are fractionated relative to the solar wind. These are Genesis data from the Genesis mission by Urivit and the co-workers. And there are 7 elements to compare to. And okay, the refractory elements all agree to very well. And the sodium and potassium seem to be higher in CI chondrites now. This trend, if there's any, would be driven by the alkali elements. What you also need to compare to, of course, is not only CI chondrites, photosphere, CI chondrites, solar wind, but it's probably also a good idea to check the solar wind and the photosphere if there's any fractionation. And among all the trends that there are with condensation temperature, I would say the solar wind to photosphere would be the best trend among the 3 options. So if you argue that there's a condensation trend for the CI chondrites and photosphere, I would say then you also have to say that there is a fractionation trend between the solar wind and the photosphere that is condensation related, which would mean that you have a dust fractionation in a solar wind where the refractories become enriched. I'm not sure how this would work, but by the same logic, if this is fractionated by that mechanism, this is fractionated too. So all this needs to be investigated a little bit more. It would be nice to have some other volatile elements like sulfur so in this data set, and maybe future data will give us more ideas about that. Now, in summary, I have a few I just go through here. We have a higher metallicity. The abundances are converging. We have asteroid samples, fresh samples, well-preserved samples, and overall, multiple representative analysis are needed to interpret the element distribution and to derive the abundances. And we will need future analysis of the sun and asteroid and meteoritic CI samples to get the full set of elemental abundances. And with that, I close and thank you for your attention.
Thank you so much, Katharina, for a great talk. We're going to start the questions now. If you have a question, please raise your hand and you can unmute and make the question and ask the question yourself. Carlos, do you see anything?
No,
Carlos has a question.
I do have a curiosity. I noticed that the distribution of the folds of the chondrite of the C1 chondrite seem to be like every 30, 40 years since 1826, and then there is like a gap between 1965 and recently findings in 2024. I would imagine that if one nowadays, right, with the satellites, with airplanes, advanced imaging from the surface, from above the surface, would one search were to be searching for these for meteorites actively, then we would be able to find more and more. But does not seem to be the case.
Well, there's a problem with these meteorites. If you don't pick them up before the rain hits, or if they hit a water body, they immediately decompose and are washed away. So I think for some meteorites, it was literally they were collected, and the next day was a rainstorm, so they couldn't collect other additional pieces. And for some other very similar meteorites, there was one famous meteorite that fell in Canada onto the ice field. So they had to make an expedition and get there, and that meteorite was partially destroyed just by sitting in the ice water. So finding the CI chondrites, it was a big luck that the recent find from last year was still surviving because it was sitting in a very dry desert. Otherwise, we wouldn't have that pristine sample. And yeah, we are all waiting for CIs to fall, and there are actually meteor networks that watch for fireballs and meteorites, and of course meteors coming down. But it's if something falls, it's some luck to get the sample.
Thank
you. Okay, I think that Vern has a question.
Yeah, one about the asteroid sample return possibilities. You mentioned that it might be possible to do the halogens from those samples, something like fluorine, which is really not well determined in either the meteorites or the photosphere.
Yes, and fluorine might be the toughest one among the halogens to get because it is a matter of the analytical techniques that are available. But as far as I know, these measurements are planned, and there's currently something going on which is called the Ryugu reference project. They only returned 5.4 grams total from asteroid Ryugu. So getting samples that are large enough for representative analysis is tough. You have to convince JAXA to fork over the sample. And that is in the works. And as planned for getting a larger hunk of homogenized rock, there is a plan to also analyze all elements, including the halogens. So this is firmly planned. I don't know what is planned for the Bennu samples. There is currently no reference project planned to have coordinated and multi-laboratory approaches for determining a representative bulk composition. We did some work in our department. Professor Kun Wang is actively involved with this, and he's actually just preparing a paper about the Bennu bulk composition. But we don't have the capability here to do a halogen measurement on small samples. So I'm actively also reaching out to experts to do these measurements.
Yeah, okay. I guess another element too, is there any hope of improving things, or is it very good for the meteorites for boron? Because that's also very difficult to measure in the photosphere. It's all buried in the ultraviolet. So
Yes, there are boron measurements coming, and there are some available for Ryugu already. Now, boron is interesting also from the geochemistry, because boron is an element that likes to dissolve in water. You might not realize it, but there's actually a fair amount of boron in the oceans. If you want to know what dissolves, well, just look at the ocean composition. So that, and there were some tiny samples analyzed from Ryugu and Bennu. Again, we wouldn't have any boron contamination difficulties or probabilities there. And some samples were found to be highly enriched in boron because there were boron salts sitting there. So this needs to be, again, measured on a representative sample and worked out to considering the geochemical redistributions.
all right, great, thanks.
Carlos Avia has a question online. He says, nice talk, Katharina. Could you comment a little about the huge difference between the new difference between the abundance for fluorine in the sun and meteorites?
Well, we did a large paper in 23 solely dedicated to the halogens. And the fluorine abundance, of course, is in the sun is from sunspots, and it was recently revised. I think it was, yeah, was it Mars et al? Both fluorine and chlorine had been recently redone. And in meteorites, the measurements are highly uncertain. I would put about 50%, 30 to 50% uncertainties on both values, solar and meteoritic. So there we definitively need new work, and I don't know what can be done in sunspots. If there's a chance to get new spectra and new analysis, and if that is being done, I would also think at the same time one should try to do some other elemental determinations to get a better reference elements for the fluorine. Say, I don't know what can you measure in sunspots. Is it possible to get magnesium or silicon from some molecule there or something? I don't know. That would be good, but I think it would be prudent to check if there's any. I would go and measure some fluorine element ratio in addition to trying to get it from the HF directly.
Thank you.
And meteorites, again, we need new measurements. The best measurements are from 1979 for fluorine. So I think there must be improvements in measurements right now, but almost nobody's doing it.
Thank you. So next question is from Daniela, please.
Hi, thank you for the talk. Can you hear me?
Yes.
Okay. I wanted to ask if based on the abundances of various elements, you are able to constrain where the CI chondrites formed in the protoplanetary disk or the protosolar disk?
That's a good one, and a lot of people have been thinking about it. In the earlier days, it was thought that the meteorites, the main source region is of course the asteroid belt, were also formed in that region. So 2 to 5, yeah, 2 to 4 AU or something like this. And now the idea is that the carbonaceous meteorites formed in the outer solar system beyond Jupiter's orbit, and the other chondrites formed in the inner solar system. And they're all also some subtle isotopic compositional differences that people can really say we have non-carbonaceous and carbonaceous meteorites. That's a whole different talk. And the carbonaceous chondrites having accreted water ice, which is necessary to do the hydration of the silicates, would form that at the largest distances. And right now, it's always beyond Jupiter's orbit. There have been ideas, and I proposed myself, maybe that CI chondrites even formed in the Kuiper Belt or beyond, simply because they're so ice-rich and carbon-rich. But there's actually no way to clearly constrain the distance at which a meteorite or a meteorite component formed. That's not really possible.
Right. Thank you for your answer. I was wondering, do you then think that Ryugu could be one of the parent bodies of the CI meteoritic chondrites?
That's another very good question. Was there one CI chondrite parent body, or were there several ones? So were all the meteorites coming from different asteroids? We have at least three asteroids that CI like. The one for the CI chondrites plus Ryugu and Bennu. They are both CI meteorites. They must be coming from a larger object, and there's actually a meteorite, a asteroid group associated with it, and the name escapes me. I think the Polana group, the Polana asteroid swarm group is related to it. There have been recent discussions. Is it one big parent body that was broken up, or several? We don't know. Again, how can you tell if these two asteroids were once one asteroid and they're smaller fragments, they got fragmented and then into near-Earth orbit? Or do all the CI meteorites come from separate near-Earth asteroids, or maybe even from Ryugu or Bennu? How would we be able to tell? Currently, that is actually several groups are looking at that issue.
Okay, thank you so much for the answer.
Okay, one more question from Carl, please.
Hi, thanks for a great talk. A lot of people right now are working on deriving abundances in the interstellar comet 3I Atlas. And I wondered from your perspective, what some of the more interesting measurements that we could look at would be, and if there are metrics that we should be going after that haven't really occurred to the cometary community.
Well, what differences would we really expect between, say, interstellar comets or different solar systems or different stars? We know that this elemental abundances is fairly consistent because it's all based on same nucleosynthesis processes. I'm talking about current generation, not low metallicity objects. And except for the metallicity, so anything in the element hydrogen ratio, which will not be solar or pristine to the system where the object might have formed in, we can't really tell much difference between any elemental abundance sets. So for the comet, even if you could measure, say, the silicon hydrogen, which you probably cannot, you might be able to measure carbon, oxygen, the volatile ices, right?
That's right.
And how do you know that these ices have not been fractionated during formation? That's the same problem we're having with comets in our solar system. Because first of all, you need to know, have these elements been fractionated during formation? And then there's an additional fractionation when these gases become released again. So I'm not sure. I would expect to see not much difference from any cometary object that we have in the solar system. I think within the range of data and abundances that you see, you wouldn't be able to tell the difference.
Thanks. That's a really good, but also very sobering answer.
Yeah, sorry. I mean, we're having the same problem that is related to a previous question. If you would look at how would you tell different objects apart from the Oort cloud to the Kuiper belt, or cometary objects formed at different distances within the solar system solely based on composition? That would be very hard. And I also don't think that isotopic compositions like nitrogen or carbon isotopic ratios would be of much help in this regard. Maybe the D to H, okay? Yeah, come to think about it, maybe the D to H. But if that were high, that could also point into yeah, pure interstellar processing ion molecule reactions. So on the top of my head and without thinking about it for another 5 minutes, that's all that comes to mind.
Thank you.
Okay, so probably one last question that is online. Thank you for a great talk. I'm not an expert in protoplanetary disks. Sea overall ratios in dust is expected to change with the distance from the star, depending on where it formed relative to the snow lines of water, CO, CO2. Is there any indication for different C/O ratio among the CI chondrites? That's from Carl Budai.
Thank you. That's a very good question. The carbonaceous chondrites for different C/O ratios, for the formation, it would be a little bit hard to tell because the whole redox state, the oxidation state, which is controlled by the carbon to oxygen ratio largely, is erased by aqueous alteration in carbonaceous chondrite, in the CI chondrites. We can, however, tell that there was a change in carbon to oxygen ratio if you look at all different chondrite groups. You might have noticed I mentioned the enstatite chondrites, the ordinary chondrites, and the carbonaceous chondrites. The enstatite chondrites are highly reduced. You have silicon in metal, you have calcium in sulfide. I mean, it's really reducing composition, and that is believed to have formed closer to the sun at a higher carbon to oxygen ratio. The ordinary chondrites somewhere in the middle, and the carbonaceous chondrites outside somewhere in the solar system. So there was most likely a gradient in oxidation state, most likely introduced by the carbon to oxygen ratio. You either had an addition of carbon in the inner solar system or a massive amount of water being removed and cool trapped in the outer solar towards the outer solar system, so that you dried up the inner solar system and made it more reducing. That's an old idea that we have discussed a little bit in context of enstatite chondrite formation, because there in the meteorite record we see that that must be a signature imposed onto these meteorites during accretion and formation. But for the CI chondrites per se, we cannot tell because the aqueous alteration erased everything. That was signatures from the early protoplanetary disk processing. But other carbonaceous chondrites tell us they were oxidized, more oxidized.
Okay, so I think, thank you so much. Thank you all for coming. Thank you very much, Katharina, for a great talk. And we'll see you guys next time, hopefully next year now, right, Carlos? In 2 months or so.
thank you for having me, and I wish you all a good holiday season, Merry Christmas, Happy Hanukkah, and Happy New Year's.
Yeah, same to you.